So this topic is energy stored in a capacitor. Now we have understood what exactly is a capacitor, what is capacitance. So we have understood that capacitor is a device that stored electric charge and electric energy. That is what we have understood until now. But how do the charge goes to the capacitor in the first place? How do the charge goes to the capacitor? That is what we have to understand. So electrical capacitor is the device to store energy, and the process of charging up a capacitor involves transferring of electric charge from one plate to another. Transferring of electric charge from one plate to another. So let's understand this in more detail. Now consider that you have two plates. Consider that you have two conductors, two plates, metallic plate, and both of them are neutral. Okay, both of them are neutral. Now, if you take a positive charge, a small dq positive charge from this plate, let's say this plate is 2 and this is 1. So if you take a small dq positive charge from plate 2 to plate 1, now when you do this for the first time, then the potential of both these plates initially was same because both of them were neutral. They didn't had any charge in the beginning. So the first time when you take the charge from this plate 2 to the plate 1, positive dq charge, you don't have to do any work. But as soon as you have transferred a charge here, positive charge, dq positive charge, the second time when you take another dq charge, now you have to do some work. Why? Because when you transfer the first dq charge from the plate 2 to plate 1, plate 2 became negative charge and plate 1 become positive charge. That means now plate 2 and plate 1 have some positive potential and negative potential. And when you take the second time, the second dq charge, positive dq charge again from this plate 2 to plate 1, now you have to do some work. So to take this dq charge from plate 2 to plate 1, you will have to do some work. Now the work that you will do will keep on increasing because once you transfer the second dq charge, the potential on the plate 1, that is the positive plate, will increase. The charge on the positive plate will increase because obviously you have transferred the second charge as well. So the potential will increase, and so the potential on the negative plate also increases. That means every time when you take a charge from the second plate, a positive charge from the second plate to the first plate, every time when you take up there, the potential, respective potential of the positive and negative both increases because the charges on the plate increases. And that is why every time you make a transfer of charge from the plate 2 to plate 1, you will have to do some more work. Every time you have to do more and more work because every time when you are moving the charge, this plate has a higher potential. Now I said you have to do more work. You have to do more work means some external agent has to do this work. This process of transfer of charge obviously is not natural. It is not going to happen by itself. Some external agent would be required to do this work. Now the external agent which is doing this work, external agent which will doing this work of transferring this charge from plate 2 to plate 1, that external agent would lose energy. You know that whenever work is done by an entity, that the one who's doing the work is going to lose energy. And according to the conservation of energy, that energy which is lost by the external entity, where did that energy go? That energy will go to the energy of this capacitor. And that is what we have to calculate here. Energy stored in the capacitor. So how does the energy stored in the capacitor? How does the energy comes to the capacitor in the first place? This is how it comes, because the very method of charging the plates of the capacitor as positive and negative would require some work to be done. Whenever you transfer a dq charge, positive dq charge from plate 2 to plate 1, you'll have to do some work because you're moving the positive charge against the electric field. This is the electric field set up by the positive plate towards the negative plate, and when you take a positive charge from the plate 2 to plate 1, you'll have to do some work, and that external agent that is doing that work is going to lose energy, and that very energy is stored as the energy of the capacitor. Now we have to calculate this expression, like what is the energy, what is the expression of this energy. Now the basic idea about the work done while moving a charge in an electric field, that we have done previously. In potential you have done that. And what was the idea? What was the concept? The concept was work done by the charge and the voltage. So W is equal to Q dV, isn't it? The W is equal to Q and dV. This formula you already know. You know that work done in moving a charge across the 2 points having 2 different potential. So the work done will be is equal to the charge transferred times the potential difference of the 2 points. This you have done before. But here in this case, the potential difference between the two plates, that is delta V, is not constant. It is not constant. Why? Why it is not constant? Because every time when you transfer a charge dq onto the plate from second to the first, the charge on the first plate, that is a positive charge on the first place, increase, and this potential increase. The negative charge on the second place also increase, and the negative potential also increase. That means every time I transfer the charge, the potential also changes. So I just cannot use this formula W is equal to Q delta V. I just cannot use this formula so easily simply by multiplying charge times the potential difference, because this potential difference is not a constant, it is variable. And I have explained it to you, whenever we are trying to equate things which are variable, they're not constant, that is where the calculus comes in. So here we have to use calculus. We have to integrate this. We have to integrate this to get the value of work done. Now, how will you integrate this, and what are you going to integrate exactly? Let's find out. So a small amount of work is done while transferring the dq charge. I'm going to consider that a small amount of dw of work is done every time you transfer this charge dq from the negative to the positive plate. And that is a work done by the external agent again. So this is small amount of work is done, and the work is done will be is equal to V, that is the potential difference at that moment, at that condition, into the dq charge that has been transferred. Now the V, that is potential at that condition, is also dependent upon the charge accumulated. What would be the potential difference between these two plates? What is the potential difference between these two plates? The potential difference between these two plates will also be is equal to the charge on the plate divided by the capacitance. This we have done in the previous topics as well, that capacitance is equal to the charge over the potential difference when we are considering multiple conductor conditions. That means the potential difference here, delta V potential difference, will become the charge on the plate divided by the capacitance. So that is where we get that the small amount of work that is done will be equal to the potential at that particular instance times the dq, that is the charge being transferred. And because V is Q over C, so then you are going to get this very simple expression of integrating, and you have to integrate dW Q over C dq. Q over C is actually 1 over C into Q. That is, C is a constant, so the C comes out of the integration. The C comes out of the integration and you have to basically integrate Q dq. So W will become integration of dW, and then that will be is equal to 1 over C integration of Q dq. What are you going to integrate? You're integrating the charge dq. So what should be the limit? What should be the limit? So the limit should be 0 to q, because dq, you're going to keep on transferring the charge from the second to the first, second to the first, and eventually you're going to transfer a total charge of q from this plate to this plate. Final, the total charge q that you're going to transfer. That means you're going to integrate this value from 0 to q. This will be your limits. When you put this value, it will eventually become q dq will become q square by 2, and you will get half of q square by c after putting the limits. Now half of q square by c, this is your energy stored in the capacitor. And how did we calculate this energy? We calculated this energy by the logic of work done in transferring dq charge from the second to the first plate, and continuously doing the same thing till total q charge is transferred. Q is equal to CV, that we already know. That means I can change this expression half of q square by c into these forms. So if you just write half of q square by c, which can then be written as half of q is equal to cv. So I can write c square v square by c, and the c cancels. So it will become half of cv square. In the same way, if you can just change the value of c, then you can also get half of qv. So all these three expressions, half q square by c, half cv square, and half qv, they all represent the same thing, that is energy stored in a capacitor. Energy stored in the capacitor. Now let's read this up. A capacitor is a device to store energy. The process of charging up the capacitor involves transferring of electric charge from one plate to another. The work done in charging the capacitor is stored as the electric potential energy. This energy is supplied by the battery. As I told you, external agent, here a battery is going to supply this energy at the expense of its stored chemical energy. So where does the battery gets energy from? And chemical energy. And once the energy is stored in this capacitor, this energy can be then retrieved. This energy can be recovered by allowing the capacitor to discharge. That means once the energy is stored in this capacitor, then if you let the capacitor discharge again, discharge means if you let this positive charge move to the negative charge by having a conductor in between, then the energy that you had spent charging the capacitor, that's very same energy you're going to get back. So that is the energy stored in the capacitor. Now we have done series and parallel circuit combination for capacitors. So let us find out that if the capacitor, if there are capacitors are in series, like this, the capacitors are in series, then does the individual energy, I hope you already know that energy is written as U, that's why it is written U as here. So individual energies of the capacitor, U1 energy of the first capacitor, stored energy in the first capacitor, U2 stored energy in the second capacitor, U3. So these are the energy stored in individual capacitors. So if I add up the energy stored in the individual capacitors, what will happen? We know that energy is equal to half of q square by c. Total energy, the expression will be half of q square by c. Just now we have done. But if I said c, what is this c? C is the capacitance, but which capacitance? Is it the capacitance of the first, second, or third, or the equivalent capacitance? So if I use this value here, that the total energy is equal to half of q square divided by the equivalent capacitance. divided by equivalent capacitance, then this equivalent capacitance itself will be is equal to 1 by C1, 1 by C2 plus 1 by C3 and so on, which is actually the sum of the individual energies. So energy stored in this capacitor is half of Q square by C1. Energy stored in the second capacitor will be half of Q square by C2, then half of Q square by C3, and you can keep on doing it. That means the total energy considering the equivalent capacitance is actually the sum of the individual energy stored in capacitors. Okay, energy stored in each capacitor. This is for the series combination. For the parallel combination, something similar, because in a parallel combination, you will have multiple capacitor, but all these capacitors are they are basically joined as a parallel circuit with the cell. Now, we already know that in a parallel circuit, the charges are different charges in each capacitor, but the potential across them is same. We know that already. If I try to find the energy of the first capacitor, I can use this half of CV square. See, I can use any formula I want. I can use half of Q square by C as in the case of series, or half of CV square as in the case of parallel. So the total energy will be is equal to half of C equivalent V square. C equivalent V square, because the total energy of the whole system would be considered when the total system is also considered as equivalent capacitance. Then this equivalent capacitance can then be written as C1 plus C2 plus C3. We already know that the equivalent capacitance in the case of parallel circuit is C1 plus C2 plus C3 and so on. So it will become half of C1 plus C2 plus C3 and so on into V square, which is actually the sum of the energy stored in individual capacitor. That is, the total energy is additive both in series and parallel combination of capacitor. The total energy of the system is sum of the energy of individual capacitor, both in series and in parallel. Okay. Now the next topic is energy density of electric field. So till now we have understood that capacitors plate positive and negative charges, and they will have some electric field between the plate, and they will also have some energy stored, half of Q square by C, half of CV square and so on. Now we have to find what is the energy density. What is energy density? So the word energy density means energy per unit volume. Energy per volume. Now where does this volume come from? I hope you remember that capacitance or capacitor, that is this parallel plate capacitor that I've made here. This parallel plate capacitor have two plates and they have some area. That is, the plate have some area, and the plate have some distance between them as well. So that is a distance between them, and this is the area of the plate. The area of the plate into the distance between them will give you volume. That means capacitor will have some volume between the plates. Any kind of capacitor, you take a spherical capacitor or a cylindrical capacitor, it will have some volume between the two conductors. This is the volume in which electric field exists. The volume in which the electric field exists. So that is what we need to find, that what is the energy stored per unit volume of this capacitor, where the electric field exists. So let's read some theory first. When a capacitor is charged, an electric field is set up in the region between its two plates. We can say that the work done in the charging process has been used in creating the electric field. Thus, the presence of electric field implies stored energy, or energy is stored in the electric field. Here we see that this particular statement is very, very important, that the presence of electric field implies stored energy, or the energy is stored in the electric field. We know that capacitor stores energy, but where does it stores the energy, or in which form it stores the energy? It stores the energy in the form of electric field. So the energy stored between the plate of the capacitor that we calculated is stored in the form of electric field between the plate. Work done by charging process and the work that has been done by the external agent, that energy is transferred to the plate of the capacitor in the form of electric field. So this point is very important, that energy energy in the capacitor is stored in the form of electric field. Now, how to calculate the energy density? We know the expression of energy, and we can obviously find the volume. So we are going to use both of these values, energy stored in the capacitor and the volume, to find the energy density, which is pretty simple. We know the capacitance of a capacitor, parallel plate capacitor, is epsilon naught A by D. Very simple. We also know at the same time that the electric field that exists between the plate of the capacitor, positive and negative plate of the capacitor, the electric field, this electric field happens to be sigma over epsilon naught, that we already know. If you don't know this, please go back and see the previous videos. Now, from this expression, we can find that sigma, that is this charge density, can be written as epsilon naught E. And the total charge on the plate can again be written as charge density times the area. This you already know, that the total charge on the plate is equal to the surface charge density sigma times the area of the plate A. And sigma you have just found out to be epsilon naught E. So the total charge Q on the plate is equal to epsilon naught E A. What is the total energy of the capacitor? Half of Q square by C. So the total energy half of Q square by C. So instead of Q, I will write epsilon naught E A and whole square divided by C. What is C? C is epsilon naught A over D. So this numerator, the whole square term, can be again written as this square, square, square. And this epsilon naught is going to cancel with one of the square. A will also cancel out. Square terms, numerator will go away. And your total energy will become half of epsilon naught E square A into D. This D will come on the numerator. Now you see this expression. In this expression, A into D is actually the volume. So I can take this A into D down, and you can write it as U over A to D will be half of epsilon naught E square. And this is what we intended to find in the first place. Energy per unit volume. That is the energy density. So energy density of a capacitor is equal to half of epsilon naught E square. Very, very important formula here. Very important formula. You will find a lot of questions from JEE mains and advanced level using this particular formula to solve electric field, capacitance, and all those. BM Sharma, DC Pandey will find numerous problems using this formula, epsilon naught E square. Now, Another interesting part of this formula is that you see the energy density is proportional to half, which is a constant. It's a number. Epsilon naught, again, it is a constant. And it is proportional to E square. That is, the energy density is only proportional to the electric field. It is not proportional to, or it does not depends upon the shape or size of the capacitor. It does not depend upon the shape and the size of the capacitor. It only depends upon the electric field, nothing else. These two are constant here. Okay, so I have used parallel plate capacitor reference to finding this energy density. But if I would have used a spherical capacitor to find the energy density, you would arrive at the same conclusion, half of epsilon naught E square. Any kind of capacitor, it may be parallel plate, spherical, cylindrical, irregular, whatever it may be. Energy density will always be proportional to the electric field that exists between the two conductors or the two plates. So it is true for the electric field due to any charge configuration. It is, although we have derived the above expression for a parallel plate, it is true for the electric field due to any charge configuration. Okay, we have derived it for the parallel plate. It is true for any charge configuration. And in general, we can say that an electric field E can be regarded as the seat of energy with the energy density half of epsilon naught E square. When we move to the magnetism, we will find that similar kind of energy is also stored as a magnetic field. Okay.